Hello everybody, my name is Lavesh and welcome to our presentation on the assignment of the data structures on the topic of the Tower of Hanoi. This assignment was made possible by Rinzing, Saiyank, Vishesh and myself. The legend. Well, this problem was created by a man named Edward Lucas, who was a French mathematician back in the 1800s, and the story goes something like this. The tower is said to be situated in an ancient city of India where monks of a temple of Kashi Vishwanath are required to move 64 golden and silver discs from one rod or needle to a third rod, using the second one as an intermediate. The discs are heavy and fragile, so a large one cannot be placed on top of a smaller disc. The monks started moving the discs back and forth, always using the intermediate disc to get a larger one on top of the third needle. It is said that as soon as the last disc is kept on the third needle, the universe shall perish and come to its inevitable end. If the monks move a disc every second, how long will it take for the universe to end? Well, the last part is a little bit abstract and not something that we'll get into right away. But what we're going to look into is how to solve and tackle this problem in a mathematical perspective. But for this, we need a systematic approach towards the problem. And that is going to be possible by the use of recursive patterns and explicit equations. First of all, you all can agree that trying to solve this legend of 64 disks by hand would be time consuming and quite impractical, on borderline impossible even. This problem can be approached a little differently by using the concept of recursion, as I just said. Well, what exactly is a recursive pattern? Well, a recursive pattern is a kind of formula that contains an initial state and then continues to have the rest of its states following a neat little pattern that can be predicted by a computer or some machine. So as you can see in this diagram, our initial state is going to be in ascending order of the disks from the larger to the smallest one, and this is going to be a final state to get all these three disks in the same order onto the third rod. Now, how do we do this? Well, we can approach this in a very practical sense. Um, so first, what we're supposed to do is look at this diagram. We have rod A, rod B, and rod C. Rod A is going to be the original rod, and the rod B is going to be the intermediate rod, and the rod C is going to be the final rod. So what we do is first we take the red disc from rod A and put it on rod C. And then we take the green disc from rod A and then put it on rod B. And then we take the red disc from rod C and then put it back into rod B. And this is the minimum number of moves that takes to move the two smaller discs from the original location to the intermediate location when you have only three discs. And there are only three moves. That's the minimum number of moves. And let's call this M. How many moves does it take to move the largest disk to the final location, which is what we want at the end, right? We want the blue disk to be on the bottom of the third rod. It literally only takes one move because we have the two smaller disks in the intermediate location. And then how many moves does it take to move the two smaller disks from the intermediate to the third one? I think you all can guess. It takes literally three moves, which is the same thing what we did initially. Now what are the total number of moves? Let's calculate it. It's literally 3 plus 1 plus 3, which is 7. Let's call this Mn. Now we can implement our generalized equation. If you follow this pattern for a couple more number of disks, maybe for 4 or 5, we can actually get a pattern which emerges as 2m plus 1. And for n number of disks, we have mn plus 1 is equal to 2mn plus 1, where m of n is the total number of moves and m is equal to the minimum number of moves it takes to move the smaller disks into the intermediate location. And as you can see in the next slide, that if there's only one disk, it literally only takes one move from the A to C. But if you have two disks, you can use the formula and get 2 into 1 plus 1, which is 3. And in M, if you can notice the pattern, that M is always the previous minimum number of moves. So for 2 it is 2 into 1 plus 1. For 3 it is 2 into 3 plus 1 is equal to 7. And 3 was the minimum number of moves for the previous turn. And for 4 it's 72 plus 1 15. For 5 it's 15 into 2 plus 1 31. and for 6 it's 31 into 2 plus 1, 63, and for 63 it is 127, and for 8 it'll be, I think, 257. Now let's come to the C++ and the coding aspect of the problem. How do we create a function or a code to actually solve this problem? How do we tell the computer to solve it? Because maybe humans are able to solve it for, let's say, even 5 disks or 10 disks at most. But if you want to implement like 64 disks or something unusually large like that, how do we tell the computer, how do we give the computer an approach to solve it? Well, you can use it by following this code. Sorry. Yeah, so basically start off with the including the header file studio.h, and all we need is that header file, nothing else. And this is going to be the C recursive function to solve the Tower of Hanoi puzzle, as you know. So first what you do is you initialize first you create a void function called Tower of Hanoi, or anything that you want, and give it 4 parameters. The first parameter is going to be the number of disks, and the other 3 are going to be rod A, rod C, and rod B, which are all char values. If n is equal to 1, now we're basically giving a parameter to the if function. If n is equal to 1, you have to basically print move disk 1 from rod character to rod character, which is rod A to rod C. And then we're going to initialize another function. We're going to basically change the parameters of Tower of Hanoi to from n to n minus 1, and from rod A is going to be remain the same, rod A, and from rod C to rod B to rod C. Again print the function, and again change the parameters back to the starting, but with n minus 1, and this keeps repeating for how many ever number of disks that we have. Well, basically what this means is, what we're trying to do over here is we are trying to move the smaller number of disks from rod A, which is going to be the from rod, to the intermediate rod, and then take the next disk from rod A to rod C, and this gives us an output for any n number of disks that we have. So now we can implement this entire problem as we just showed you in the diagram. We can implement this in the main function by initializing int n is equal to 3 as an example, Tower of Hanoi n, which is going to, and now we can put in the proper parameters of n, which already we have n is equal to 3, and then a, c, and b, which are the names of the rods, and then finally end the code. Now we have the output where n is equal to 3, n is equal to 4, and n is equal to 5. These are the number of steps that we need for all these 3 items. Obviously, as you can see, n is equal to 3 has only about 7 moves in it. N is equal to 4 has about, 15 moves in it. And n is equal to 5, I think, has about 31 moves in it. And this literally confirms our pattern that we derived earlier. Perspective. Now, we looked at the entire mathematical perspective and we were able to derive a code out of it as well. Now let's try to tackle the symbolism of this problem and see how the numbers actually mean. Well, in the original problem, it said that you need 64 disks. And how long would it take to arrange 64 disks if the monks were able to move 1 disk per second? Well, if they were able to somehow tirelessly continuously do this, how long would they take to move the 64 disks in order from rod A to rod C? It can actually take about an unbelievable amount of time, which is 5 into 10 to the power of 11 years. If you want to compare that to the age of the universe is only 5 into 10 to the power of 10 years old, which is like 33 times as long as the universe's age. This is an insane amount of time, and practically it would be quite impossible for one monk to do it all alone. The computing, now if you want to compare it to computers, well, let's say that a computer can process about 1 billion moves per second. Let's say it could do 1 billion, it can move 1 billion rings or disks per second. And if it want to do 2 into the power of 64 moves, that would take literally over 500 years. So you would require an insane number of computers to do this, or or you just need a really more powerful computer. This really puts a perspective on the value of exponents and time as a construct, and it just shows how insignificant human beings can be in the face of the universe. That brings us to the end of our presentation. I thank you all for spending your time to listen, and these are the cited sources that we were able to really get inspiration to complete this presentation on ourselves. Thank you so much for listening.